Welcome to the lecture video for page 25 of the Math 1 packet. A few things just to remind you of. The first one that pops up on this page is this concept of direct variation. We've seen direct variation on a few problems in the last 10 pages or so, but I just want to remind you that a relationship characterized by direct variation has two characteristics. One is that it has a constant slope. So if you graphed it, it can't curve, it can't be parabola, it's just got to be a straight line. And the second characteristic is that it has to go through the origin, meaning the point 0, 0. Let's just do a couple of quick examples of direct variation and things that would not be direct variation. If I graph it, this would be an example of direct variation. It's a straight line and it goes through the origin. This would not be an example of direct variation because even though that's a straight line, meaning it has a constant slope, that line does not go through the origin. So that's not an example of direct variation. Although that one goes through the origin, it obviously doesn't have a constant slope. The slope increases for a while here, then it starts to decrease a little bit, then it increases again. So the slope is not constant, hence not a direct variation. A word problem example could be something like the perimeter of a square. So if we want to find the perimeter of a square, we know the equation for that is simply going to be the length of one side multiplied by 4. So the perimeter of a square is just 4s. So if we were doing it on a nice little graph, we could put P on the vertical axis for perimeter and S on the horizontal axis for the side of the square. And you can probably see from this equation pretty easily that it does go through the origin. We know that because there's no y-intercept. In our little equation, P equals 4s, the y-intercept would just be plus 0. So that does go through the origin, and it also has a constant slope of 4. When the length of the side increases by 1, the perimeter has to go up by 4, which makes sense because there are 4 sides. So that's what the graph would look like. Clearly it has a constant slope and it goes through the origin, so that is an example of direct variation. There's a problem on page 25 that asks you to identify whether or not certain relationships vary directly. And actually as part of it, it may help to remember a few formulas about a circle. You probably know these, but we'll review it real quickly anyway. The circumference of a circle, aka the perimeter around a circle, is always 2 pi r. The diameter of a circle, we'll just do a quick little graph here. And so the circumference is just the distance around the circle. The diameter of the circle is the length of a line that goes through the center of the circle and connects both sides. It has to be a straight line. And the diameter is therefore also 2 times the radius. Radius, of course, just being the distance from the center to the circle, and that's what classifies a circle. A circle is actually all the points that are equidistant from the center, aka all the radii have to have the same length. Well, notice if you look at these two, another formula that you might see for the circumference is simply pi d, or pi times the diameter. Since the diameter is 2r and the circumference is 2 times pi times r, we can rearrange those and just call it pi times the diameter. And the area, of course, is pi times the radius squared. Next topic, just a quick little reminder of algebra blocks. Again, algebra blocks, they seem a little strange. You may or may not have seen them before. But once you play around with them a little bit, they're actually really, really helpful. And they represent this whole idea that the multiplication of two numbers is really just a way of finding an area of a rectangle. And when you can put those two ideas together, your understanding of both becomes much stronger. I just want to look at this one. I want to use algebra blocks to multiply the quantity x plus 1 times 3x. Now I've already represented one side, so maybe we'll call this the height of a rectangle. This length is 1. You can probably see that's one block on my graph board. And then I just called this x, since x can be anything. Well, if I wanted to represent the other side as 3x, one way to think of that is simply x plus x plus x. So if I just to make it look nice, it appears that my x is about 2.5 squares long. So that would be 1x here. And another 2.5 squares long would take us to about here. And one more 2.5 would take us about here. Again, you don't have to draw it out perfectly to do the algebra block. But I think if you do set up the right proportions, it does help you see what's going on a little better. And now obviously I can create all of my smaller blocks, because this is simply just the quantity x plus 1, and this here is the quantity 3x. So multiplying those together should be the same thing as finding the area of this algebra block. And we can find each one. This height is 1, so this little rectangle is simply x times 1. That's x times 1, that's x times 1. These are all x by x, so the area of these small rectangles, or in this case squares, are all x squared. When I add all the areas together, it looks like I've got 3x squareds, and I've got 3x's. And if we use our rules about the distributive property, this should work out nicely also. If we distribute the 3x over both of those terms in the binomial x plus 1, I think we should get 3x times x, or 3x squared, plus 3x times 1, or 3x. And thankfully, these guys both match up. So a nice demonstration of an algebra block to remind us how to distribute a monomial, such as this, over a binomial, such as this. One final reminder, a little tip about dealing with fractions in equations. So in this scenario, we've got x over 3 minus 2x over 4 equals 2 plus x over 12. There's probably 7 different ways you can solve this, but I think some are easier and more efficient than others. Whenever I see fractions, if you don't like dealing with them, an easy way to get rid of them immediately is to multiply both sides of the equation by the lowest common denominator. So in this case, we've got 3 and 4 and 12. Well, obviously 3 and 4 both go into 12. So if I multiply both sides of this equation by 12, I should get rid of the fractions. You just need to be careful though. Remember, we multiply both sides of the equation because that will still make it equal. If this side equals this side, and I multiply both of those things by 12, then whatever appears also needs to be equal. I can't multiply just one side by 12. That wouldn't be true. If you were the same age as your best friend and we doubled your best friend's age, you would no longer be the same age. So you've got to multiply both sides of the equation. Now just be careful, each term needs to be multiplied by 12, so we have to multiply that term by 12. But 12 divided by 3 is simply 4, so this would be 4x. Now when I do 12 times this term, 12 divided by 4 becomes 3. 3 times negative, don't forget the negative here, 3 times negative 2x should give us negative 6x. Remember, this is separated by a plus sign, so we need to multiply the 2 by 12 as well. That'll give us 24. And when I multiply this one, the 12 divided by 12 is simply 1, so all we're left with is x. You'll notice this becomes pretty easy now. We can just bring all the x's on one side. 4x minus 6x should be negative 2x. We've still got 24 plus x. We subtract x from both sides to get negative 3x equals 24, and finally divide both sides by negative 3, and we should get that x equals negative 8. Quick, easy way to get rid of the fractions from the beginning, usually making your life easier. You could have also, put both of these over 12, lowest common denominator, done the subtraction, put that over 12, cross multiplied. That obviously also works, but a little trickier. Remember my tip: if it's a test though and you have lots of time, do it both ways. Just make sure you don't make any simple mistakes on the first method. You should be all set for page 25. Have fun, and I'll see you tomorrow.